In this problem, we looked at the concept of a perfect set. Okay, so we are dealing with perfect sets, and basically what we want to show that a perfect set is not countable, it's uncountable. There are many proofs out there on the web that one may find, but there is a bug in the proof. So during the proof, I will tell you exactly where one has to be very careful about what's out there, okay? And how to fix it, of course. So first of all, so we take P, a subset of R, and we say that P is perfect. We assume, of course, P non-empty, otherwise, okay, is perfect if and only if P is equal to P prime, it's been Cantor Dixon derivative. So, number one, we know from this that P is closed because we have seen that P prime is closed. And if P prime is equal to P not empty, then P is infinite. Okay? Great. So now assume that P is countable. So we're doing by contradiction. So in this case, P is going to be equal to x1, x2, etc. And we assume that xi is different from xj for I different from j. Okay? So now how do we show that our contradiction? The idea is, so we need P closed for sure, and this is how we're going to do it. So let me just show how to do it with x1, and from there you will get the idea how to build this by induction. Okay? So first of all, we go to x1 minus 1 and x1 plus 1. This is a neighborhood, and we intersect P. Okay? So we know that this will have plenty of what? Of element. Okay? So the mistake is to assume that x2 is here. x2 may not be here. Okay? And so the way to do it is, we know that there are a lot, so we're going to go till we reach the first one. Huh? So meaning, so x2 may or may not be. So assume that x2 is not in this set. So we'll call it I1. In I1, or P1, sorry, let's call it P1. Because P1. So it's not in P1, okay? And assume it's not. If it is, we stop. So we go x3 not till we reach the first one. So we have xn1 minus 1 is not in P1, but xn1 is in P1. Okay? So some of them the proofs are out there assume that n1 is equal to 2, basically. Okay? In other words, we stop at 2. 2 is not there, x2 is not there, but so we have to be careful about this step. Okay? Great. So what happened now? Then, so here is to see it. You have x1 and you have xn1 somewhere. The other ones are not here, but xn1 is somewhere. So for the sake of illustration, let us say that xn1 is here. Okay? And so what we are going to do, we're going to have a small interval, an open interval, centered around xn1 inside the first one. Okay? So this gives me, so we'll call this first open interval u1, and this one we'll call it, or okay, let's call it u0, and then we go for u1. Okay, we'll see, u2. Okay, so what happened? The closure of u2, if you take the closure of u2 of the interval, okay, you are still inside use 0. Okay? Great. So now, what do we do? What do we have? So now we have, so we found this one. Okay? This is your U2. Okay? This is your U1. And what do we have? We have U2 bar is in U1. And U2 bar intersect P is not empty. Okay? Great. So now we start again from xn1. So from U2. So we have xn1, which is the center of U2. Okay? And now you look at xn1 plus 1, etc., etc. So you assume that it's not. If it is, you stop. Huh? It is not in U2 intersect P. And you keep going till you reach N2. So it's not in U2, okay, but xn2 is in U2. Okay? So again, you will find an interval, open interval, round xn2 such that U3 is inside U2. In fact, even the closure of that interval is inside, even the endpoint will be inside U2. Okay? So if you keep doing this, we will build these intervals UN. So these are sequence of open intervals centered around some xn's, some xi's, yeah, and such that un plus 1 bar is in un and un intersect p bar is not empty because they're centered in p and un element, some element xi. So now what do we have? We have a decreasing sequence of closure segments, intervals. So this un bar is a closed interval. Okay, inside with en un plus 1 bar, they're getting smaller. Okay, and they intersect P. Now it's very important to say that P is closed. So here P is closed. Okay, and you have your un bar intersect P not empty, and they're decreasing. So now we can use the intersection of the un bar intersect P, and remember these are bounded intervals, so this is all bounded. So they are bounded intervals closed, so we can use a compactness argument. So a compactness argument, okay, to say that this is not empty. Pay attention also that we can tweak this by having these UNs, the length is becoming smaller and smaller. So in this case, we can also use the completeness of the real line and show that this intersection is not empty by using the completeness of R, because if you choose an element in this set here, then this sequence will be quotient, then it will converge, and the limit will be in that intersection. Okay? This is very important when you want to go to compact matrix spaces and show that, in complete matrix spaces and show that perfect sets are uncountable. So the argument works this way. You're not going to use the fact that the compactness argument, but you can use the fact that these UNs are just metric balls with radius becoming extremely small. Therefore, what you have there is you can use the Cauchy argument with the completeness to show that this intersection is not empty. So now let us show that this cannot be this is not possible. Why? So let xi in this intersection. Okay, so the way we build it, see, the way that we build the UNs, it will avoid all of, see, in the UN, if you look at UN, okay, this one does not contain, so here is included in UN minus 1, the opening interval, and this way you can say from this assumption that xi in fact belongs to all of the UNs here for every n. But this is not possible. Why? Because the way we build UN, okay, this UN avoids, okay, x1 all the way to xn. Okay, the way we build it, it avoids all of them. Sorry, n minus 1. Okay, so if n is greater than I, then xi is not in UN. Okay, which is our contradiction. Okay, and therefore your set P cannot be countable, so is uncountable. So next we want to show that the Cantor set is not countable. We know from the little lecture I did that the Cantor set is uncountable because, so this is the case of the Cantor set, C. So we know that C in fact is in bijection with 0, 2 to the power n, and we have seen that this set here is not countable, and therefore C is not countable. We have seen this, okay? That's one way to prove it. But in fact, we can also use the previous results. Why? Because we claim that C is perfect. Okay? We know that it is closed. So why is it perfect? Because we have seen that for every x in C, okay, if you look at the triadic expansion of x, it's equal to 0, comma, in the base 3, of course, a1, a2, a3, etc. And the ai's are all equal to 0 or 2, right? So what we can do is to show that, in fact, you can find elements which are different from x and that get closer and closer to x, okay? So how do you do that? So first of all, um, we assume that the sequence, for the sake of, so we have two cases, huh? Either, okay, x, it stops, and then it stops, okay? So in this case, we take x, I'm sorry, so let's call this one k. So xn for n greater than k, okay? For any n greater than k, we take xn equals 0, a1, all the way to ak, and then we keep putting zeros as much as you want, and then you put here a 2, for example, and then you do it. So for sure, xn is different from x, and the distance from x to xn is less than uh, 2 over 3 to the power n. Okay? So, and for any n large, okay? So this will tell you that you can find element closer to x, different from x, as close as you want, okay? And otherwise, if, okay, x is equal to 0, comma a1, a2, and it never stops, okay, it never stops, then it's enough to take just a1, a2, an, 0, 0, 0, and then you have the same argument that x minus xn is less than 1 over 3 to the power n. Okay? So, or I'm sorry, 2 to the 3 to the power n. That's the maximum we can get anyway, the 2. And again, xn is different from x. Okay? So this way, for every epsilon, okay, we are able to find there exists an n such that x minus xn will be less than epsilon. It's enough to take n large enough to have 2 over 3 to the power n less than epsilon. So you see the x minus epsilon, x plus epsilon intersect C, the Cantor set, is not empty and has elements different from x. Okay? So this tells you what? That C is perfect and therefore C is uncountable.